we can also hold particularly imperfect messages. Yeah, I don't know what that is. It gives all these options.
Oh, I see.
Yeah. Live stream jiggles.
I guess this was the server stuff. We're good?
Yeah.
Okay. So, all right, so I think we'll start off this time talking about bridge splits. So, I believe that's what we're talking about tangles. Okay. So, B bridge chain. Maybe give this a name, B for now. A link as a decomposition. And we split the link or the three manifold link pair into two pieces. Each of which is a trivial tangle, and they meet along a common sphere sigma. So the pair B sub I, T sub I, each of these is a trivial B tangle, B bridge tangle, with the boundary equal to the sphere sigma appointed, the marked sphere sigma xb. Okay, and we call sigma the bridge sphere, and we call x of b maybe we'll call these bridge points. Okay. So of course it should be clear from this that xb, I guess, is L intersects sigma. That's what we mean by the bridge points. Okay. So let's look at an example of this. Oh, let's I was gonna say something. Okay. So to give an example, what I should give you is sort of two tangles that whose boundaries are identified. So I'll sort of draw this two ways. The first way I'll draw it will be like this. Colors. So this is a perfectly nice tangle, B1T, and then another nice tangle over here. This one looks like that. And then, so, I need to get this later. So the way we want to think of this, though, is that these two tangles are identified along the bridge sphere. So really, especially in this dimension, we can draw these. Oh, I left something out of that. Okay, so we can actually think of B1 is sitting up top, and then we can think of B2 is sitting down here. Okay, and then the caveat here is that actually what we want to write is B2 T2 overline, which I actually wanted to include in the definition. And what we mean by this is we mean the tangle B2 T2 with the opposite orientation. So in general, MN bar denotes MN with the opposite orientation for any pair of manifolds. Okay. So if we weren't really too concerned about orientations to begin with, this wouldn't be much of a problem. But it's useful when thinking about sort of diagrams of pairs of tangles or eventually triples of tangles, to remember that if we sort of think of these as independent objects on their own and we draw them as such, that when we take their union, we need to remember to take the opposite of one of them.
But mirroring is not built into that, is it? Orientation.
Yeah, I guess it is built into it because when we think of S3L, or we think of S3 as the union of two 3 balls, we're really thinking of one of these as being the standard 3 ball and one of them being the 3 ball with the opposite orientation. So really we should be writing something like that because the orientation that this induces on the boundary 2 sphere points, say in maybe, and this one points out. And so we have to be careful about the orientation of the ambient manifold. And that doesn't have to do with orienting the codimension 2 manifold. But what it does do is it induces a mirroring this union like this. So changing the orientation of the ambient manifold is what corresponds to taking the mirror of the submanifold, whereas changing the orientation of the submanifold is not really affected.
Another way to say that is that the orange picture on the bottom on the right is a picture of B2 T2 bar precisely because mirror reflection across the horizontal plane from the upper half plane to the lower half plane is an orientation reversing diffeomorphism of one ball to another. So in other words, that really is a picture of the first thing you had followed by an orientation reversing diffeomorphism.
And maybe I can draw it one more time just to So if we reflect, this is supposed to be a plane, I guess. There's a plane in between those planes that we reflect through. And then we get the mirror down here. This is B2, T2 bar, and this is B2. Yeah. So a little tricky to keep track of, but the safe thing to do is to sort of remember. Just so that we keep it on. Any other questions about that? Okay, let's see, there was another comment I wanted to make. Oh yeah, I think this is probably something that belonged in the last lecture. I didn't really talk about like projecting onto a plane, a tangle onto a plane, did I? In the last lecture. Okay. Yeah, so given tangle BT, we can project onto a not really an equatorial disk. I don't really want to think of it that way. but more, this is a funny thing to call it, but and maybe this doesn't make sense without a frame of reference anyway, but some sort of longitudinal disk to get a planar diagram. Okay, and so let me explain what I mean by this. Oh yeah, so then let's give it a name. Let's give it a disk E. A disk E with the boundary of T contained in the boundary of. Is this what I want? I think I want to sort of make this condition. Okay, so let's look at an example of what I mean by this. So here's our ball, and then inside here we have some tangle. Let's draw something like this. So that's some tangle in the ball. It's probably trivial. Yeah, maybe. And the disk that I want to actually project on is sort of actually implicit in this picture. It's sort of E is the intersection of B3 with the black one. If you think of this sort of giving a three-dimensional aspect to this by expanding the blackboard, and we sort of get this, which is just like a knot diagram is proper. So now we have some diagram of the tangle. Maybe we still denote a T. And then what we can kind of do is maybe then we take we use some sort of projection, stereographic projection or something to and then okay, this is going to be a little difficult. So this is going to then cause this to do something up, over, under, this one. This one goes under. So I think you get something like this if you cut this over. Okay. Anyway, so this is what I would call a planar diagram for a tangle. And so this, maybe this involved a couple of choices, like exactly how we choose E. Although I guess, yeah, if we specify that it contains the points, maybe that's not such a big deal, where we cut open. But I think the upshot is a reference and leaves the three-dimensional picture behind. And this sort of drives home another point which I didn't really emphasize, which is when you're considering trivial tangles, you really need to consider them relative to some fixed points on the boundary sphere, right? Because if you're allowed to move the points, then you can undo all of the nature of the trivial tangle. And so from now on, we'll sort of always think about our two sphere as sort of being spread out flat here on the bottom. And we'll sort of remember a sort of canonical labeling of the bridge points along this two sphere, which here is sort of represented as boundary of the disk E with E sitting there. So there's maybe some things to be said to make this a little bit more formal, but let's not belabor that too much right now. In fact, I mean, to emphasize that it's maybe not as big of an issue as we might be worried about, unless you run into trouble, but I was basically already doing it here, and nobody was really too bothered. Right? I mean, I was already depicting these tangles as planar diagrams, and we saw sort of implicitly that the union of two planar diagrams of tangles is a planar diagram, provided we remember this orientation, this mirroring convention. Okay, so hopefully that's more or less okay. Any questions about that? All right, so this is the definition of a bridge splitting, and this is sort of an example, and implicit in this example was a lot of conventions about how we think about these things. We consider two bridge splittings B and B prime for a link to be equivalent if, so again, there's going to be a couple of equivalent ways of saying this, but I'll say if there exists an orientation preserving diffeomorphism F from S3 to S3 such that F, I guess the restriction of F to the ball BI from BI T to BI prime TI prime is a diffeomorphism of pairs for I equal 1 and 2. Right, so basically it's a restriction on the notion of two links being equivalent, where all we ask for two links to be equivalent is an orientation of pairs. Here we ask that it preserves the decomposition, giving the bridge splitting. Okay. So, equivalently, we could ask that there's an ambient isotopy of S3, which takes the pieces of this bridge splitting onto the pieces of this bridge splitting. Another way to phrase it is we can ask for a diffeomorphism of the pointed sphere S2 or sigma comma XB that extends over each of the tangles. That's another way to ask over each of the tangles. That's another way to ask about it, or to think about it. Okay. So in another equivalent definition, which I'll write this one up. Equivalently. So let's set up some notation we haven't had before. Let's let E sub L denote the link exterior, and we'll let sigma sub L equal the bridge surface sigma intersect the link exterior. So this looks like some meridional surface, right? We take sigma sub L is now going to be some punctured surface, some punctured sphere. Okay, so we have that B and B prime are equivalent or isotopic. AF is isotopic to sigma L prime in the link. About these surfaces, we can isotope coincide with the outcome. Okay. Yeah, so in particular, two equivalent bridge splittings have to have the same number of bridge points, right? They have to have the same value B in order to be considered equivalent. Might be, well, yeah, I guess in this case we want to say that would be isotopic. Yeah, of course. There's this issue of the difference between considering these types of objects up to isotopic versus up to diffeomorphism. But because we're working in a fixed manifold, fixed copy of S3 here, probably the right notion is isotropic. We'll talk more about that later. Okay, any questions? All right. Okay, I think I won't say anything more about it. Okay. So definition. Elementary perturbation of B at, say, a point X. I think now that I write X, I'm going to forget now. Okay. So an elementary perturbation of a bridge splitting at a point in the collection of bridge points is the following local modification. Okay, so somewhere in our bridge splitting, we have a point X, which has sort of a piece of tangle 2 going down and a piece of tangle 1 going up. And the local modification, which can be reversed, is to change this into, I think, I'll call this X, X prime, and X double prime. Where we introduce a new bridge arc to either side of the bridge, to the bridge sphere. And these bridge arcs come with sort of nice little obvious bridge spheres, or membranes, bridge discs, which can be chosen in the complement of the other bridge discs. Am I at the end of the sentence yet? I think I am. So an elementary perturbation of B is this local modification. So the perturbation is going in that direction, and then we maybe call the reverse direction deperturbation. And maybe I'll just remark, this is sometimes called stabilization. Stabilization and destabilization. Of a bridge splitting in the literature, it's commonly called that. But we'll use these words for something else, so we'll refer to perturbation, what's going on with this move. All right, so the first thing to check then, I guess, which I'll just write down as a lemma, I guess, or an exercise, is to claim that the result of an elementary perturbation is a new bridge splitting of the link and is independent. Is it EMC? I had to ask my pre-calculus class spelling questions like that today. It's independent of the choice of bridge point X. Okay, so a good thing to to try to work out, to make sure that you're wrapping your head around this stuff correctly, is to check that it didn't matter which one of the bridge points I chose to do the elementary perturbation. I'll get isotopic bridge splittings regardless. Okay. So I guess the definition then sort of continues once we verify that it's well defined, and we say that or maybe I'll just say, we call B prime a perturbation, or we call B prime perturbation or perturb of B if it is the result of a sequence of perturbations. Okay, so that's pretty obvious grammar. And then more importantly, two bridge splittings.
So you mean distinguish between that or perturbations and deperturbations?
Oh yeah, that's.
Do you want that to be an
true.
equivalence relation?
What?
Do you want that to be an equivalence?
Yeah, let me write this one.
Okay.
Yeah, two bridge splittings, B1 or B and B prime are stably equivalent. So here we do sort of reserve the notion of stabilizing these things. Stably equivalent if they, or I think I phrased it correctly, if there is a bridge splitting B plus that is a perturbation of each of B and B prime. Okay, so they have a common perturbation. Two bridge splittings are stably equivalent, or they have B. They have a common perturbation. Actually, for various reasons, that might actually be a better way to say it. Okay. All right. Any questions about that? Hopefully, I'm not obfuscating this too much. It's a little kind of some technical nomenclature at this point. Okay. So here's the proposition to get us going with some of this stuff. So fix a bridge splitting B for S3L given by the decomposition S3L equals B1 to T1 means sigma X B B2 T2. I guess you could probably denote the we could, so I don't know if I want to do this, but we could denote the by a triple, maybe B1, B2, sigma. So by a triple of submanifolds of S3. Okay, so the bridge splitting is determined by this term. Maybe we'll adopt that convention. I don't know. Okay. Then following our equivalent. So the first thing is that B is perturbed Okay, so perturbed just means, I mean, if it's not clear, perturbed means that B is obtained from some other bridge splitting by an elementary perturbation. So what is this equivalent to? There exist membranes delta, say delta naught psi, for strands. Let's do it like this. Delta naught psi for strands Ti inside their respective tangles. Ti such that delta sub 1 and inside delta sub 2 is in the bridge points. Okay, so just to be clear here, because it probably could have said a little bit more. When I say there are membranes for these strands, well, I guess we saw last time that such a membrane could be completed to a membrane system. That was sort of implicit in the proposition that was over there on the board last time. So yeah. So anyway, so maybe that's not as big of a deal as apply. But this is saying we can find membranes that intersect in a single point, just like we had here. Okay, so in the notation of this proposition, we have given a perturbation, we can find this. This is delta 1, 0. And this is delta 2, 0. And they can be seen to intersect precisely in a point which is contained in the boundary. Okay, I guess I should say that. X, that's true. If we know, if we can find such disks, then we're okay. So that's not too complicated. And then there's another equivalent way of saying this, which I'll just mention because it seems to be useful sometimes, but it's slightly different. There is a membrane delta 1, 0 for T sub 0, 1 inside T sub 1, and a curve delta in the exterior of the bridge points. A curve in the exterior of the bridge points such that delta intersect delta 1, 0. Delta is sort of a weird name for this curve. Let's change it to, let's just change it to C. There's a curve C that precisely a point, and C bounds a disk in the exterior of the second tangle. Okay, so I'll give you a chance to write that down, and then we can see what I mean by that. There's nothing really complicated going here. Maybe even just belaboring this a bit too much. But like we saw last time at some point, there's this regular neighborhood of one of the bridge disks that we can take where we get this disk. So this would be the curve C, and maybe this is the disk D sub C, which I didn't name over here. And what we see is that the curve C intersects the bridge disk delta 1 not in precisely a point. So what we're sort of looking for is a compressing disk on one side that intersects a bridge disk on one side. All right, so there's nothing fancy going on in that proposition. All right, so the importance of the perturbation operation is the following theorem, which was originally proved by Berman in 1976, I think, the right attribution. Any pair of bridge splittings for a given link have a common perturbation. Okay, so this is, I don't think I'll say anything about the proof. There were various places where it was observed that one way to prove this, which is maybe not quite what Berman did, although I'm not quite sure, is that you can show that the Reidemeister moves can be realized by by ambient isotopy or I guess we should call it maybe bridge sphere isotopy. Ambient isotopy is preserving the bridge sphere. Bridge sphere isotopy plus plus perturbations. So you just sort of use the fact that you can go between any two link diagrams using Reidemeister moves to show that given a sort of had appeared previously, you can go between any two diagrams of this form using just sort of Reidemeister plus then also perturbations of everyone increase the bridge index and allow you to use some more moves. Yeah, Bill?
So every two bridge splittings are stably equivalent?
Yes. Yeah, I decided, I've already thrown out stably equivalent as what I want to say. Yeah. Stably equivalent, maybe it could be interpreted as meaning there's a sequence of perturbations and deperturbations that relate any two bridge splittings. When really there is a priori stronger statement, which is that there is just.
So what's not obvious is that stable equivalence is an equivalence relation. Because if it's not obvious that stable equivalence is an equivalence relation. I mean, it would be obvious with some thought, but in other words, stable equivalence means you go up and then you down. Stabilize, destabilize. Like one climb up and one climb down.
Yeah.
And then if you string two of them in a row, you climb up again and climb down again. And it's not obvious that stabilizing, destabilizing, stabilizing, destabilizing can be achieved by just stabilizing first and then destabilizing.
You were saying it's not obvious that it's the same equivalence.
It's not obvious that is an equivalence relation at all. But the transitivity, I guess.
Oh, I see what you're saying.
I mean, I don't think it's hard, but.
Yeah, I think I know what you're saying, but
I'm saying if you stabilize and destabilize and then
it's common
stabilize.
perturbation which is not obvious in equivalence relation. Because when you compose them, it's not a common perturbation.
Right, exactly.
Are you okay? I think you're saying.
Yeah, stable equivalence is the same thing as having common perturbation.
Oh, I see. Okay. Yeah. Okay. Yes, I agree with that. Okay. Yeah, so this gives us sort of a nice picture of the sort of space of bridge splittings, or the complex. I guess it's more of a complex or graph even. Splittings. Maybe I'll come over here and sort of drop. So we have all these levels corresponding to different bridge indices. Maybe I'll start this example at 3 because that's where things sort of seem to get exciting. and you can just sort of record how many, and you can record how many bridge splittings a given non-core link has at one level. So maybe maybe the guy we started with has two splittings, two distinct non-isotopic bridge splittings of index 3, but that they become isotopic after a single perturbation, right? But on the other hand, once you get up to bridge level 4, the link actually has a handful of new non-isotopic bridge splittings at level 4, which aren't perturbations of, or aren't perturbed. And then maybe these two become the same, but maybe the other ones all stay distinct after perturbing. And then what do I have going on here? I guess at some point, maybe there's even a new one there. But at some point, things have to sort of become the same. And then after this, we have a unique bridge splitting at each level. Okay, so
That's also not obvious from what you said.
yeah,
Like
maybe I'm making a claim here that I don't quite want to make. Maybe all I want to say for now is this is a possible example, an a priori possible
In
example.
principle, you could have new ones all the way up.
Right. If I stall for 5 minutes, I won't have to address that issue. Okay, I'm going to state some important results from the literature that give us an idea of what these actually could look like. So these are theorems. Okay, so the first one is due to Berman and her paper. And she proved that there exists a composite three-bridge knot with a non-isotopic bridge splittings, three bridge splittings. And at the same time, Montesinos, at the same time, same thing, but we produced a prime knot, prime three bridge knot that admitted distinct splitting. So a little bit more interesting of an example. And then fast forwarding to more recent times, Zhang showed that there exist three bridge links. With infinitely many distinct three bridge splittings, distinct up to isotopy, and he classified them. Classified such three bridge links. And then recently, even more, or I guess this is a bit more recent, it was less recent. Alex Howard showed that a hyperbolic knot has only finitely many distinct bridge splittings.
For fixed bridge number or all together?
I don't know. I didn't clarify that in my notes. What did he say? Well, I mean, I guess it wouldn't really make sense to say all together because you can be stabilizing.
Yeah.
So
yeah,
I'm guessing that the result is there are finitely many at each.
That's right.
At each level. Yeah. And then right before class, I was looking at some results that I actually didn't know existed until Alex alerted me to it. But I didn't have time to write down what they say. But they basically say that even among, say, 3 bridge knots, you can see some pretty interesting behavior here. For example, they give 3 bridge knots that have a 3 bridge splitting, and then also a non-perturbed splitting at bridge number n for any n above 3. So you can sort of have these things arbitrarily far apart. And they haven't, I forget the statement of the other thing from that. So probably next time I'll clarify even a little bit more what's done here. I'm pretty sure it is unknown whether or not a knot can have infinitely many non-perturbed bridge splittings. But I don't know. I didn't know about these papers until this afternoon, so I'll have to look into that. Okay, does anybody have any questions about that? Oh, okay. So I think I actually have time to write a few more results on the board here. Here's some more theorems. And these theorems are of a different nature. So Hotel proved that the unknot has a unique one bridge splitting.
What is there? Isn't that up?
Oh, sorry. Sorry, you're right. Yeah, has a unique non-perturbed bridge splitting. I guess it's maybe another way to say, a better way to say bridge splitting. In other words, every bridge splitting of the unknot for beat greater than 1 is perturbed. In other words, it's true. Its graph of bridge splittings just looks like that. You call that a one thing. He also proved that the same result for 2 bridge knots. That was actually written kind of funny in my notes. So I'll have to check, but every 2 bridge knot emits a unique non-perturbed bridge splitting, so same result, and then fast forward, Ozawa, torus links admit a unique so in my notes, I have all of these written as having that they admit unique minimal bridge splittings. And so I guess the theorems I just wrote on the board are all stronger, except in this case where I think that's actually right. So I'll have to double check. But the last thing I'll say is that all of these results are approachable using the same results that I referred to these papers of Schulten's, right? These papers of Schulten's have these 2 lemmas in them where you put these ancillary surfaces in a nice Morse position with respect to your height function, and you start simplifying their critical points. And using similar techniques, you can recover these results. So I guess I should probably revisit the last 2 panels on Friday. And on Friday, I'll prove something. Maybe I'll prove like that you can get between 2 bridge membrane systems with jumps, or I'll prove something else maybe that I have just been skipping over. So if you want to think about the proofs of these things before then maybe I'll be ready. Okay, that's all.